Welcome to Chapter 5, Periodicity and the Electronic Structure of Atoms. In this chapter, we're going to consider a few interrelated topics, such as, how does light behave? What does the answer to that question tell us about atoms and electrons? How can we describe the behavior of electrons in atoms on this basis? And, why is the periodic table that weird shape? Let's start with that first question, how does light behave? Interest in the properties of light goes back thousands of years, but by the late 17th century, scientists had determined that light was made up of waves. Like any waves, water waves, sound waves, or whatever, we can describe light in terms of wavelength, frequency, and amplitude. The simplest example of a wave is a sine-like wave, such as the one shown here. The wavelength of any wave, abbreviated with a Greek letter lambda, is the distance between wave peaks. The frequency, given by the Greek letter nu, is the number of wave peaks that pass through a given point per unit of time, and the amplitude is the wave height, measured from center to peak. In the context of light, what we see as different kinds of light are waves of electromagnetic energy with different wavelengths and frequencies. This includes things like different colors of visible light, but also other types of light outside the visible spectrum, like infrared radiation, for example. Examining the spectrum of different types of electromagnetic radiation, we get a chart like this. Wavelengths are shown along the top axis and frequencies on the bottom axis. Notice that they have an inverse relationship. As one increases, the other decreases, and vice versa. Only a small portion of electromagnetic radiation, from wavelengths of about 380 to 780 nanometers, are visible to the human eye. You can see here the correspondence between different wavelengths and what we perceive as different colors. At longer wavelengths than visible light, we have infrared radiation, often used to generate heat, microwaves, including the waves used in microwave ovens to cook food, and radio waves, including those used in AM, FM, and other types of radio transmissions. At shorter wavelengths than visible light, there are ultraviolet radiation, including wavelengths that can cause sunburns and skin cancer, X-rays, including those used to produce medical X-ray images, and gamma rays, which are typically generated by decaying radioactive atoms. Light waves, like any type of wave, behave according to the equation that the wavelength of the wave multiplied by its frequency is equal to the wave's speed. In the particular case of light, the speed in a vacuum is abbreviated as c and has the constant speed of approximately 3.00 times 10 to the 8th meters per second, regardless of the type of light involved. For context, that speed is extremely fast compared to the speeds of normal objects you encounter in everyday life. It's 200,000 times faster than the fastest rifle bullets, and so fast that light can travel around the entire Earth in about 7 times in a single second. Here's an example using the equation relating speed, frequency, and wavelength. One of the main frequencies of light given off by mercury-based street lamps has a frequency of 6.88 times 10 to the 14 inverse seconds, or hertz. Same unit. What's the wavelength in nanometers? We can rearrange the equation to solve for the wavelength, lambda, and we get c over nu, or the speed of light divided by its frequency. Plugging in the value of c and the frequency provided in the problem cancels the seconds unit, leaving us with a value with units of meters. To convert to nanometers, we effectively multiply by 1 billion, or 10 to the 9th power. This gives a result of 436 nanometers. If you go back to the slide that shows the spectrum of visible light lined up with each color's wavelength, you should see that 436 nanometers is in the blue region of the spectrum, so this answer makes sense. Now, if light is made up of waves, we should expect it to physically behave like other types of waves, so like sound or water waves, for instance. All waves should be capable of producing diffraction and interference phenomena. Diffraction refers to the bending of waves around an object or a small opening, and interference refers to the ways that waves can overlap with each other. This can happen with both waves lined up in phase, which amplifies the wave, known as constructive interference, or it can happen with the waves out of phase, causing them to cancel each other out, which is known as destructive interference. And sure enough, electromagnetic waves behave as we would expect. When a beam of light, such as a laser pointer, passes through a screen with two adjacent slits, an interference pattern is created. Alternating bright and dark spots show up on the surface the light is pointed at, where the bright spots are the result of constructive interference, and the dark spots are due to destructive interference. As I said, light's wave-like properties have been known for over 400 years. But is there more to the story than that? The short answer to that question is yes. The somewhat longer answer is that, in certain experiments, light works in a way inconsistent with normal wave behavior. Several related cases of this discrepancy were found in the late 19th and early 20th century, but one that is particularly compelling is the photoelectric effect. This is the observation that irradiating a clean metal surface with light causes the metal to eject electrons. That isn't surprising on its own. Light waves carry energy, and that energy can kick electrons off of atoms. What is remarkable, though, is that this can only occur when the light used is above a certain frequency, which varies depending on the particular metal. In other words, even a huge amount of lower frequency light can't eject any electrons, while a relatively small amount of higher frequency light does cause electrons to be ejected. An analogy that might be helpful here is that of a ball hitting a window. A single baseball is easily capable of breaking a window, but a bunch of, say, ping pong balls wouldn't be, even if you have so many ping pong balls that they have a larger combined kinetic energy than a single baseball. The implication of the photoelectric effect, then, is that light energy is carried in some sort of discrete packets or quanta. This is not the normal behavior for waves. The experimental data shown here demonstrates this. For a metal, the number of electrons ejected is 0 below a threshold frequency of light. Higher intensity light, with a frequency above the threshold, can cause more electrons to be ejected than would be the case with lower intensity light, but no level of light intensity can cause electrons to be ejected if the frequency of the light is below that threshold. This leads to the conclusion that the packets of light, known as photons, each carry an amount of energy that depends on the frequency. That equation is shown here. The energy of a single photon, E, is equal to h, Planck's constant, value shown on the screen, multiplied by nu, the frequency. In other words, light energy is directly proportional to the frequency of a light wave, and unlike a normal wave, that energy is carried by discrete or quantized particles, known as photons.